Hey guys, in this video, we're going to talk about section 1.7, and we're going to be able to solve problems using modeling. So, anything with these functions that we've had up until now, we're just going to try to compile all of the information we know into one thing. So that's really all there is to it. I don't really have notes for you other than just working some examples and showing you how we can model with some of the functions that we've learned about. So in our first one, it says we're going to suppose that the track of the spread of a virus among a population is what we're studying, okay? They said we're going to sketch a graph of the number of infections in as a function of time t. So what we want to think about here is what type of relationship are we working with? Okay, so I'm thinking let's think of just like a plain old graph if we think of what's actually happening. So when it comes to the spread of a virus, we have this patient zero, okay, the very first person to get sick. So this is not going to start at zero. At time zero, we have our very initial person, okay? And then that one person gets sick, and that one person infects other people. They don't just infect one person, usually. This person will usually infect multiple. And each person that they infect will infect multiple people. So, this is one of those situations that we would call like exponential growth. Okay, it would follow that exponential growth pattern, just going up. However, we need to think about what's actually happening over time. At first, that's the pattern that's going to happen. But we have a cap on our population. We do not have an infinite number of people. I mean, we could argue that we have we continue to, the population grows because people continue to have babies and all that jazz. But usually a virus is going to spread a little bit quicker than people have children. So when we talk about the spread of a virus, we're going to talk about us having like a cap, a population cap, where if I was going to talk about this virus growing, if it kept going in this trend, eventually it's going to hit that max amount of people. But we need to talk about really how is that virus going to work? Is it logical to assume that every virus is always going to be 100% transmissible? Where we could say like there's 100% of the population that would get that virus? No, most likely, most viruses are not like that. Usually, there are a group of the population who never end up getting that virus. There's people who have yet to get COVID, right? So when we talk about this virus spreading, we can talk about the fact that, yeah, it's going to start with that exponential growth, but as time goes on, that's not going to continue to go up in that same trend. It'll continue to increase, like the number of people who are sick will continue to increase, but it's not going to increase in that same way. It will continue to increase, but never actually end up hitting that max number. Now, this, if we looked at a full graph of what this would look like, this would be more along the lines of what we call our logistic function. Again, this is not necessarily 100% accurate. This is just an eyeball of what's actually going on. And this side of the graph is not really that important because we're not looking at negative time. But the type of graph that starts off this way, and it starts off as concave up and then flips and becomes concave down in this manner and then approaches that cap but never actually hits it, that's the type of function that's modeled with a logistic function. So, although this thing started off looking like it was going to be exponential, when you think about what happens with that virus over time, it doesn't continue in that exponential trend. And that's the logistic trend. So that's one of those types of graphs that we studied back in section 1.3. If you're asking like, where did you get this from? 1.3, go back and look at it. We had a function called logistic. Okay, so what we're going to do here is explain because that's what they want. So we're going to say, although this relationship appears to be exponential at first due to the finite population and over time, the growth is going to slow down, which is also kind of showing in this function. So although due to the finite population and the slow of the spread over time, the relationship is best modeled with a logistic function. We'll say graph. Okay. I know that's a long explanation. You can always reword that, but I wanted to make sure that we had a good explanation here as to why we didn't just go with exponential and leave it at that. It really is more of a logistic type of situation, because if we look at it over time, towards the end of the virus's life, that spread will slow down, and you don't necessarily reach 100% of your population. Okay, so that's the type of thing we're looking at here. Now, I'm also going to throw out there, like, not every single type of problem is going to be the same. If you were to look through all the different problems that we have in our textbook on this section, all of those problems are very different. So let's do a problem that's very different. That was one where all I needed was to give you the graph of the model. But what about if I were to ask you for something else entirely? Okay, so here, the first one was more of a graphical model, but in this problem, we're actually being asked to write a algebraic model because they want a function that represents the area of a circle in different ways. Okay, so very different. First thing you're going to have to remember is, how do you find the area of a circle? Well, area of a circle, most people remember the formula pi r squared. So I want to talk about how that relates to what we're dealing with in here. The equation area equals pi r squared is in terms of your radius, r squared, right? So that actually gives you the function that they want for part A, where they want this in terms of your radius. This would be the function A of your radius r. That's pi r squared. That's all we need. But when it comes to writing it for our diameter, we're supposed to figure out, how do the radius and the diameter compare? Well, my radius equals half the diameter. We know that, okay? And if my radius is half the diameter, all I need to do is take this, which is my radius, and plug it in for r. So my radius in terms of my diameter would be pi times my radius squared. Just instead of an r, we're putting d over 2 because that's what the radius is. We can clean this up a little bit. So if I square this fraction, it would become d squared over 2 squared, which is 4. And it's a little bit of a nicer way to write this if we were to write it with the number first and then the variable second. So really, we can think of this as pi over 1. Well, this would clean up to write as pi over 4 d squared. That 4, I just kind of picture it as like the 4 sliding over. But really, it just comes from when you multiply the fractions out. Okay, it can clean up and look that way. Okay, last one of these. We're going to look at, what about in terms of circumference? Well, have you ever wanted to go directly between the area of a circle and the circumference of a circle? You may or may not have. In your in your geometry class, you probably did. What we can do is we can actually create a function that allows us to go directly between the two, so that you're not having to first solve for the radius and then plug it into the other formula and do like multiple things. If I come up with an equation that allows me to go directly from one to the other, it makes things a lot quicker. But one thing we have to know is what the circumference is. And we know that the circumference is 2 pi r. Well, I'm able to actually solve for my radius by dividing both sides by 2 pi here. And you might be saying, why is that important? You'll see. So these pi's on the right and that 2 will cancel. And what we know is that our radius is equal to the circumference divided by 2 pi. And we can take this and plug it in just like we did on the last part. When we knew what the radius was here, radius equals diameter divided by 2, we took that and turned it and plugged it into the original area formula. I can do the exact same thing here. My radius equals circumference divided by 2 pi. So if I do area of my circumference, right, I can do the pi times my radius squared. C divided by 2 pi squared. Just like on the last one, I'm going to work on cleaning this up a little bit. So this is pi, but c squared would be c squared. 2 pi squared would be 4 pi squared. And another nice thing that will happen here is this pi is over 1, and that pi will cancel with one of these pi's down there. So it cleans up just a little bit more, becomes c squared over 4 pi. Remember how I said sometimes it's nice to write the number first and the variable second? This is the same thing as 1 over 4 pi c squared. If you wanted to go directly between your area and circumference, this formula would allow you to do that, which I think is a pretty neat trick. All right, so that's that. We got one more problem, okay? And this problem is a bit of a doozy. So I would encourage you to probably pause the video and maybe draw some of this stuff out, okay? Write it all out. What we have here is talking about this box. And they've got this piece of cardboard that they're turning into a box. They cut off the little corners, okay? And when they cut off the little corners, it allowed them to fold those pieces up and make a box out of it. So your picture does not need to be gorgeous. Your picture just needs to be something that you can reference, okay? And be able to maybe draw on for a second. So it does not need to be anything spectacular. Mine definitely is not. And it won't be when I go through this in a second, okay? So what we're dealing with is we're asked to find a bunch of different things about this. The first thing is that they want us to figure out a volume as a function. Now I'm going to bring this up here and kind of redraw this because I don't want to draw all over my normal notes page, but we're going to mark it up with some values that we know. They told us in the beginning of this thing that my original piece of cardboard was 8 by 15, right? Now, the little pieces that they cut, the measurements are x by x, x by x, x by x, right? Just like that. So when I cut those pieces out and I fold these pieces up, that ends up being the side of my box, right? This piece right here is this piece right there. Okay, so when I'm talking about the measurements or the dimensions of my box, this is not saying that this is 8 inches wide right there, right? Because we cut off these little pieces that are X inches long. So how can we come up with an expression to talk about this length in here? The best way is if I know the whole thing is 8, right? This whole side is 8, and we have X into X. This piece would be 8 minus 2X, right? X plus X is 2X. If I take the whole thing 8 and subtract off that 2X, that would give me what's left, and that is the width of my little box right here. All right, another thing that's important is when I cut off these little pieces, X, and I fold it up, this becomes the height of that box, right? This gets folded up, becoming the height. That's what x would be. So that's another important piece of information. And then along this way, I know that all the way across is 15. This is x and x. So here in the middle, this would be 15 minus 2x. So this gives me dimensions for my box. And when it asks for me to write the volume of this, right? Remember that volume is length times width times height. So for part A, where it asks me to write the formula for the volume as a function of x, I'm going to say v of x to give my function notation. And all we're going to do is take these three dimensions and multiply them out. So I would have x times 8 minus 2x times 15 minus 2x. Ta-da! Just like that. Okay, next part says find the domain of v as a function of x. So they said to note the restrictions. Okay, if I look at my function that I already have, algebraically, there is no limit to what that x value could be. Technically, if I was going to throw this function into a calculator and graph it, there would be all real numbers for my x's graphed. If you were to look at that table of values, there's nowhere where x could not be a value. So in theory, algebraically, my x would be all real numbers. However, because this is not just talking about in theory, this is talking about a very specific circumstance where we're dealing with a geometric measurement, we have to be careful. X is talking about the length of a side of a box. Okay? And because of that, we have to think of what type of restrictions do we have? Well, my length is not going to be a negative length. That would be nonsense. It also is not going to be 0. That wouldn't make sense either. So when it comes to talking about my domain, x could be greater than 0, okay? But it's not going to be less than or equal to that. Another thing that we want to think about is what is it possible for x to be? Is there a limit to how large x could be? So I think about back to my box. If this whole side is 8, right? It is not possible for this x to also be 8 because we have, if that was the case, we'd have 8 and 8, and that would not make sense. You think about what is the maximum value that x could be in this circumstance? Well, if this was x and that was x, right? Then the largest value for x I could have would be maybe 4. This could be 4 and 4. That would add up to 8, but then I wouldn't have anything in here. So I don't think it could even equal 4. I'm also thinking about looking at your equation in here. What would cause this to be 0 in either circumstance? If x was 4, 2 times 4, right? 2 times 4 is 8. 8 minus 8 would be 0. 0 is not going to be a side length. That doesn't make sense. But it could be anything under 4. What if it was 3? That would be okay because 2 times 3 is 6. 8 minus 6 would tell me that this was 2 inches wide. That's okay. That would still be a box. So I would say that this is anything up to 4, not including 4. I also could write that as inequality notation. I have seen some of you guys doing that. Nope, not equals to. So I could write it as 0 is less than, x is less than 4. That would be fine. But it would not include 4 or include 0. Okay. Now that we have that, they said graph this as a function of x over the domain. You can use whatever graphing calculator you prefer. It does not matter to me. But what I would do is take a moment and type it in. Practice doing that so that you're comfortable, okay? And I would honestly just type it in exactly how you see here. You don't need to make it any more complicated than that. It is already complicated enough. So when I do that, I'm using my NumWorks calculators. You can use whatever one you like, but type it in, looks like that. I'm going to go up to my graph, and we can see what this graph looks like. Now, remember how we said that our domain is going to be looking at from 0 to 4. We're not going to look at anything outside of that because it would not make sense in the context of this problem. Okay, so we're only looking from 0 to 4. And on this question, it says that we're going to find the max finder to find the max possible volume, which means we want to find this maximum point up here. Okay, on my calculator, I'm just going to go up to the calculate section. So I'm going to tab up and over to the calculate, hit OK, and select maximum, and it finds it for me. It's this value right here, my max finder. Okay, I'm going to write this out. My max finder, it says that I have the X value 1.66 repeating. Okay, then we have my Y value is 90.741-ish. Okay, so this is 1.667, 90.74. I think that was, 741. So they said use your max finder, done, to find the max volume. So which one of these is going to be our volume? Remember that my function, v of x, v is my volume, right? And whenever you have a function f of x or v of x or whatever, that's indicating your y. So what I want you to notice here, okay, my volume, that is my y. So when I'm trying to find my maximum volume, I want my y value. So max volume, that would be 90.741, and this is inches cubed. Okay? All right, part D, last bit. How big should the squares be cut to maximize the volume? Guys, what value talks about the side length of the square? That's x. So when they say what is the volume or the value for the, what dimension should the square be? That square should be that x value from that max point. Okay, my square should be measuring 1.667 inches by 1.667 inches. If my squares are equal to that, if that's their dimensions, then I will get the maximum possible volume out of that box. Okay? So I know that was a whole lot. Yes, that question is complicated, but it's not anything out of the realm of what we can do. We can do a question like that, even though it is more challenging. Okay? So, take a picture of that or write down in your notes, take pause. Here's the solutions that we had to it. And yeah, that was a tricky question, but you can totally do it. Guys, these are the types of things we're looking at in 1.7 with modeling. It is all over the place. There's so many different types of questions that you can have. So this is just a few, just to give you an idea. But we want to be able to take all the stuff that we have done and be able to apply it to a singular problem. So, all right, good luck on this, guys. I will see you in the next one. Bye.